All right, recording is rolling. Welcome to Tuesday, a new week because we had yesterday off. So, a bunch of guys just turned in your EM and optics quiz. So, thank you for doing that. We'll get those graded pretty soon. This week it's going to be relativity. So, theory of relativity, talking about Einstein relativity. We'll look at mostly special relativity. I'll mention general relativity a little bit though. Tell you guys what this is about, a little bit of the history behind this, some demos and examples. Here's all the topics I want to cover this week. I don't know if this might be a little bit ambitious for a 4-day week, but I'll see what I can do. And I'm not going to give you guys a quiz on this, but clipped to the right side of your desk is a page that has a gear on one side and gear in the mirror. And on the other side has a bunch of questions about, well, mostly special relativity again. Okay? A little bit of math energy equivalence. So this page, I'll go over this with you guys. We'll do a few of these today and then talk about this experiment a little bit. And this page, I'll eventually pick up a grade. And so instead of a quiz, as long as you follow along with me step by step, then they're right there. Oh, and then next week, I want to do some SAT math prep with you guys because I know there's SAT coming up. Almost all you guys in here are going to take it, and the math specifically I can help you guys out with. So that is next week's plan. All right, let's get going. So, do you guys remember a week or two back? I was telling you one of the first ways that the speed of light was calculated was that there was a Danish astronomer. I think his name was Ole Romer. That's the pronunciation. He was looking at Io orbiting Jupiter. You guys remember that? And he said, well, as Earth heads towards Io and Jupiter, it looks like the frequency of that orbit increases, and as Earth heads away, it looks like it decreases. You know, there's like plus or minus 13 seconds per orbit. And he was able to use that, and he came up with the speed of light is about 2.2 times 10 to the 8 meters per second, which actually isn't that far off. Our modern day understanding is 3 times 10 to the 8 meters per second. So where did we get the modern 3 times 10 to the 8 meters per second? And ultimately, how is this going to connect to relativity? So in the page that you guys just picked up from the right side of your desk, that of course I'm eventually going to pick up from you guys after I go this year. On one side, okay, you guys see this toothed wheel and a mirror. So I hope you guys solve this exact problem as it's laid out here later this week. But this is the experimental design that actually really accurately nailed the speed of light. And this goes back to 1849. So this guy named Hippolyte Fizeau, and what he did was he started this toothed wheel, and say he has this this light source behind the wheel, maybe like a candle flame, something just representing something like a light source. And also on the side of the wheel is I'll draw like an eyeball to represent kind of vision, right? So you're looking through. Okay. And you're looking through the gaps in his teeth, and you're watching this light beam go from this candle flame through the gaps in the teeth off to this mirror that might be like a few kilometers in the distance. And it's going to bounce back through. Okay, and so you can see the reflection of the light source in the mirror. Okay, so that's all fun and good. Now, of course, any light rays that hit one of the teeth are not going to pass through at all, but if it goes through the gap, it can come back through the gap and it's all good. Okay, then what he does is he gives this thing a spin. It speeds up spinning. Now, the fact that light does have a finite speed, I mean, crazy fast, but it is finite, okay, means that it's going to take some time to go to this mirror and back. This mirror might be a few kilometers in the distance. Okay? And maybe if this wheel is spinning fast enough, then wouldn't it be the case that, well, again, any light rays that hit the tooth are not going to go through at all, but let's say a light ray goes through the gap, just like you see right here. That by the time this light ray gets back, you know, a few kilometers this way and a few kilometers back to the tooth wheel again, if this wheel is just turned a few degrees, just enough that this tooth has covered the adjacent gap that the light could go through, the light is not going to make it through back the other way. And so what would you see, say, from the side of the wheel? Well, you would see a blocked image. You wouldn't be able to see the reflection of that, that light source anymore. Okay? At some exact speed, right? If it's going too slow, maybe you'll see like look like sort of the doors closing on the light, but you see part of it. If it's going at just the right speed, then it would be completely blocked. And what he realized is that there's enough information lying around there. Say if you know, well, look, I gave you some numbers here. Maybe something to do with the number of teeth on the wheel, how fast you're spinning it, yada yada. There's enough information lying around. If you do some calculations, you can figure out what that very fast but still finite speed of light is. Now, when we eventually get to this paper later this week, I'm saying, well, from the future, you know what the speed of light is. So the question is ultimately going to be, how fast did he have to spin the wheel? But of course, he was doing it in reverse. He was saying, I'm spinning the wheel at some speed. Now, can I calculate how fast the speed of light would be? Right, so he does that, and he comes up with about 3 times 10 to the 8 meters per second. So pretty much what we accurately understand to be modern day. Okay, so great. We got the speed of light back in 1849. Now, you guys have learned a bit about waves the last few weeks, and one thing that you've learned about waves is, for example, the sound wave that you're hearing my voice with right now. Well, it needs a medium to go through, like sound is a pressure wave, and if you took out all the air and there's a vacuum in this room, you wouldn't be able to hear me at all. You guys know that. Now, I have told you guys that light can travel through a vacuum, but people didn't know that back in the day. They said, okay, well, light is a wave. They kind of figured that out. So there was this understood general knowledge that turned out to be false, but I'll tell you guys why in a few minutes here. They thought that there would be some kind of what they called a luminiferous ether that light would travel through. They thought there had to be a medium for any kind of wave to travel through. And since light was a wave, there must be some kind of medium that carried that wave. And they called it a luminiferous ether. Now, if you've never seen this before in a science book, that's because it's since been disproven. Again, I'm about to show you guys how that was. But this is sort of like a ripple will carry on a water wave, or you guys can hear me because of the medium of air between me and you, or something like that. And then they think, well, if there's this luminiferous ether, think about what that would mean in terms of like the motion of the Earth and our motion relative to it. Because here's the Earth, okay? North Pole, South Pole. The Earth is spinning about 1,000 miles an hour at the equator, right, relative to the pole. But then that's not all. Of course, here's like the sun way in the background. So got some perspective going on. The Earth, of course, is also in orbit around the sun. So going around, so that's a really fast speed too. And that's not the end of the story either, of motion, because the sun is, and our whole solar system is in fact in orbit around the Milky Way galaxy. You get a picture of like a spiral galaxy. Okay. Not together. So, okay, so we've got all these different motions going on. And if there is such a thing as a luminiferous ether, then we're probably moving pretty quickly relative to that. So you can do some back of envelope calculations, get a pretty good estimate of what that speed would be. Now, around this time, 19th century, we can make a little bit of a detour and come back to this idea. Let me flip my screen and show you guys something that is a bit beyond the scope of this class, but just to get an idea across here. There's this guy named James Clerk Maxwell who wrote down these 4 equations that describe all electromagnetism. And these are them right here. Yeah, this is again beyond the scope of this class, but if you guys ever major in physics and go like grad level physics, then be very familiar with these. But some of these are, yeah, what you see here is, you guys see the C, it's letter C? So that represents the speed of light. So the speed of light is embedded in these equations. And one thing that these equations imply is that the speed of light is constant, which everybody thought was kind of weird, because they thought, well, hold on, how could the speed of light be constant if there is such a thing as a luminiferous ether, which they assumed there was, and you could move relative to that? Well, there seemed to be a contradiction there. But they thought, okay, well, maybe we can explain that away, because maybe that constant speed of light is relative to a stationary ether, or like if you're moving along with the ether. So that was the interpretation for a while, but something maybe not exactly adding up, that they could sort of maybe explain it away. Okay. Then, so back to this part of the story. In the 1880s, there was this team of scientists that conducted this really famous experiment called the Michelson-Morley experiment. So Michelson-Morley. There were different versions throughout the 1880s, but let's say 1887 is kind of where it all comes to a crux. And they want to, this team of scientists wants to figure out what is either the speed of the luminiferous ether, or maybe what is our speed relative to it. If you've got all this tight motion on the planet, the sun, right, everything spinning and revolving, and right. So they figured out a way you could actually do this, and their experimental rig looked kind of like this. So what they had was some light source. I'll represent that with a candle flame, but some kind of light source that would be sending out these light beams. And so send a light beam, say like that way, for some particular light ray. And then here it was split by a half silvered mirror. So this caption middle represents, you could call this a half silvered mirror. I've also seen it called a splitter. Okay. So half of this light is able to just pass through, okay, but half of it gets bounced off at a 90-degree angle because the mirror itself is at a 45-degree angle. Okay. So part of it gets reflected, but going this way, and part of it passes through. Okay, so that's all fun, good. But then you put a couple of mirrors at the end of these arms, okay, and the light gets reflected back. Ba-boing, ba-boing. Okay. And then yeah, part of this ray gets reflected 90 degrees this way, and then half of this ray passes through. So you have a couple of rays that then end up on some card in the back that looks like this. And this distance is equal to this distance. And you might look at that and say, well, didn't those two light rays that eventually meet here have to travel the same distance? And that would be true, right? Because here's the path of one. Boing, here's the path of another. Boing, boing, boing. Right? But what this team was thinking was that if we were in a luminiferous ether, they should actually meet at this card on the endpoint at slightly different times, and therefore you should see some kind of interference pattern. And I'll show you guys why they thought that would be the case. So hang tight on this. This is coming back. But I'm doing a side note here to show you their thought process behind this. Right, so I have to go back and tell you guys about a problem that really intrigued me when I was in high school and I was studying for the FCAT. Back in high school, I was studying for the FCAT. Okay, and let's say you have, say, some water here. Okay, I'm going to make this one a lake. Okay. Here's a lake. Okay. And I'll make this one here a river. And I'll have a river current flowing this way. I'll say the speed of the river current is like 5 meters per second, left to right. Okay. And let's say we got a couple of boats. So I have a boat here, a boat here. Okay. So let's say you and me, we've been in lots of boat races before. We're pretty evenly matched. We can each paddle with a speed of about 10 meters per second, and it's always a tie. But then we get to these couple of bodies of water and say, yeah, we have some stagnant water here, and we have some flowing water here. Hey, let's have a boat race, except maybe one of us will be in the lake and one of us will be in the river. And what we're going to do is, see that tree down there at the end? We're each going to paddle to that tree and around and back. And this could be like our start-finish line right here. So start-finish line. Okay. And whoever passes start-finish line, okay, it's going to win the race. Okay. So whoever gets there first, round trip, right? Down the lake and back, or up the river and back. So that round trip. Another way to say who wins the race is who completes that motion in the least amount of time. Okay. So give you some other numbers here. Let's say V paddle is the same for both of us, or paddle, row, whatever. We can go at 10 meters per second. The lake, of course, is just stagnant. The river is flowing at 5 meters per second. left to right, that'd be downstream. Oh, I'll give you guys a distance. Let's say the distance from the start finish line to the tree is like 150 meters. And just to throw you some numbers. Now, what I'm trying to get at is like who's going to win the race? The boat in stagnant water or the boat in the river water that's flowing. It doesn't matter what numbers they make up. The answer is going to be the same regardless. You always have the one particular body of water. You'll always win on that side. Let me see what you guys are thinking. Let's see, show hands. Who's going to win the race? The boat in the lake or the boat in the river? Who thinks that the boat in the lake is going to win the race? Boat in the lake. Who thinks it'd be the boat in the river? Okay, so see that 50-50 split. Okay, well, let's run the numbers. Right? Now the boat's a bit easier to calculate. Distance equals speed times time, right? Distance equals speed times time. Okay. Now, the speed relative to the land is the same speed as the paddling speed because the water isn't moving either, which is just going to be 10 meters per second. I see 150 meters one way and 150 meters back. So isn't that a total of 300 meters? Going at 10 meters per second for some amount of time, divided down 10 meters per second. Looks like that time is going to be, for the round trip, right, there and back, looks like 30 seconds. Okay, so great. Know that if you're in this boat paddling as hard as you can there and back, it's going to take you 30 seconds, 15 there and 15 down. Right? All good? All right, let's check it out for the guy in the river. Now, paddling upstream, would there be a relative velocity of 5 meters per second to the shore because it's 10 minus 5, right? So that'd be 150 meters. So we're still doing it, x equals vt. Okay, but I need to split this into two halves. 150 meters at only 5 meters per second because 10 minus 5 for some amount of time. Looks like that time is going to be, what is 150 over 5? I'm looking at 30 seconds. Okay. Then it comes back downstream, the other 150 meters, but this time he's getting a boost from the current. Right? And if you thought, well, maybe the guy in the river wins the race, you probably think, well, maybe there's some advantage from going at 15 meters per second for half the race, because 10 plus 5 for some amount of time. Now this time comes out to 10 seconds. If you add the two together, right, 30 seconds one way, 10 seconds the other way, you get 40 seconds. Okay, so this guy's time is 40 seconds. So now if you compare these two, right, in the lake it was 30 seconds round trip, and the river it's 40 seconds round trip. Right. So yeah, if you thought you would win the race in the lake, you are correct. And again, it could have made any river current, it wouldn't have mattered. It could have made 1 meter per second. You still win the race in the lake. So another lesson you can draw from this is that if you are ever running a race, if you pace yourself, you'll tend to win the race. Versus if you like sprint really fast and then come back slower, right? You'll tend to lose the race. Okay, so is that all right? Is that? Yeah. So if you maintain a constant speed, you actually get the faster. All right, now let's go back to this Michelson-Morley experiment. So now remember that they are hypothesizing that this luminiferous ether exists. It was sort of common knowledge that it did, even though we know today it doesn't. And they were trying to figure out, well, what is the direction of this thing? So what they were thinking is, for example, what if the luminiferous ether had a velocity that was like to the right? Maybe it's like west to east, or I don't know, just for example. They're thinking, well, what that would mean then is that the light ray that follows this path, well, this leg of the race, it's sort of analogous to that boat in the lake, where it's not moving relative to luminiferous ether. So velocity, luminiferous ether, versus the light ray that gets bounced this way. That's kind of like the boat in the river, where it's going against it for a while and it's going with it. Okay, which means that it should take more time for it to travel against and with the ether than it would orthogonal to the ether. Yes, sir? So that when the two rays line up, they actually, when they meet this card, they will be out of sync, out of phase, and there should be some kind of interference pattern. Okay? Now that's what they were thinking. And they think, okay, well, we can make certain measurements on this interference pattern, then we can figure out what the speed of the luminiferous ether is, and also the direction, so the total velocity. Okay. What they got was actually, and this is sometimes called like the most successful failed experiment in science. They did not get an interference pattern at all. And it did not matter how they oriented this thing, right, north, south, east, west, or a 45-degree angle. It didn't matter what latitude they did this at. It didn't matter how they oriented this experiment. They kept getting the same results over and over, which showed that there was no luminiferous ether. So one of the assumptions that have been going around for a long time that there was such a thing that light carried on. When I say that light can travel through a vacuum, this is the experiment that established that. Okay, so we got, there is no luminiferous ether, light travels through a vacuum. Also, it travels at the same speed regardless. I mean, this is another thing, is you might think, well, I mean, the Earth is spinning, so shouldn't there be some kind of effect at all of like an east-west motion of light? No, like nothing. Light travels at a constant speed regardless of your motion. Let me show you why that is also really weird. Let me talk about Newtonian relativity. Now, when you say Newtonian relativity, that's different from saying just relativity. When you say just relativity, like, hey, we're going to study relativity this week. The implication is Einstein relativity, which we're getting towards. But let's just go back to basics here. Let's say there's a car in motion, and the speed of the car is like 20 meters per second. And you were up here, say on the roof of this car, and you got a baseball, and you can throw the baseball at a speed of like 30 meters per second relative to you, or relative to still ground. Okay? Well, what if there's a guy out here, say with a radar gun, measuring what is the speed of the baseball? Okay? What does this radar gun read? The speed of baseball is what? It would be 30 plus 20, which is like 50 meters per second. That'd be true, right? Or what if this guy turns around and throws the baseball back the other way? Relative to the ground, wouldn't it go 30 minus 20 would be 10 meters per second backward? Right. So that would be relative velocities, kind of like we did for the boat in the river. But here's the weird thing. If this car turns his headlights on, and let's say breaks out this toothed wheel and does the whole toothed wheel experiment and measures what is the speed of light, say relative to the car, relative to the driver in the car, okay? You'll get the speed of light is 3 times 10 to the 8 meters per second, regardless of how fast the car is traveling. Okay. And then if this guy in an inertial frame of reference just off to the side also does the same experiment with the tooth wheel, he will also measure the speed of light is exactly the same number, 3 times 10 to the 8 meters per second, regardless of your frame of reference. Huh. So that's weird. The speed of light actually does not add up the same way the baseball did, right? Now, people sort of had all these pieces of information lying around by the end of the 19th century. And there was something funny that didn't quite add up, but they didn't really know what to do with it. Okay, well, that's interesting. The speed of light is the same no matter what. But they didn't know quite at that time what to do with it. Right, this is where Albert Einstein enters the picture. So he's a patent clerk working at a Swiss patent office. So all day, every day, his job is just to think very deeply about how mechanical things work, cross-reference and see has this ever been invented before, sort of thing. And he's thinking about experiments like the Michelson-Morley experiment, like the simplification that speed of light, no matter what, looking at those Maxwell equations. And Einstein finally cracks the puzzle and realizes something's going on that nobody had realized before. And this is really weird, so I'm going to show you guys this twice. Right? I'll show you guys this in notes, and then I'm going to flip over to an animation, so you get to see this twice. Right? So it goes like this. Let's say that there's like this train car. So got this box car, put little train wheels on it. And inside the train car, say there's this guy standing here. He's got a watch on. He's timing the whole thing, and he's got this light on the ground, like a flashlight, some beam of light. And there's a mirror on the ceiling, and there's going to be a light ray sent straight up, and boing bounces straight back down, boing just like that. Okay, and it travels some distance up and down to do that, and it takes some amount of time. There's this guy times on the stopwatch. And that time I'm gonna call T naught. Okay, so the amount of time to, actually I'll just do like a one-way distance from the floor up to the ceiling. It would be T naught, the time takes, okay. But yeah, let's go back and talk about one of the very first things you ever learned in this class, probably back in August, which is if you are inside this boxcar, can you feel if this train car is even in motion? Or if it is, how fast it's going? Can you feel if it's 30 or 40 or 50 miles an hour? No, you have no way of knowing that unless you can look through a window and say relative to something on the outside world. Like right now, we're whizzing around the earth really fast, but we can't feel it because just inertia, right? You feel changes in motion, you feel forces and accelerations, but not just pure velocity. So maybe there's some guy outside the train car, and he's got his own stopwatch on too, and he's timing this whole thing. Okay. But he notices something that the guy inside the car doesn't notice, which is that this whole car is in motion with some, I'll just call it V. So V could be the speed of the car. Okay. So as time is passing, the car goes from its original position to like somewhere off to the right. Okay. My picture is going to be exaggerated quite a bit beyond anything that's quite realistic, but it'll get the geometry across, get the idea across. Okay, so here's this train car in motion. Okay, the guy inside the car, of course, got his stopwatch on. Whole deal. Okay. Now, this guy outside the car is maybe watching the same beam of light. Maybe we take off the side panel and watch this beam of light. What does the beam of light look like according to this guy outside? Well, the beam of light doesn't go straight up and down. It goes off on a little diagonal. Now, here's where I'm going to massively exaggerate this picture. Let's just get the idea across. I draw a flashlight back around here. The beam of light, according to the guy outside the train car, makes a path that goes something more like this. There's boing, like that, right? Makes that type path because it's not just going up and down, it's also traveling on speed v to the right. Right? So each of these guys sees the beam light going some distance in some amount of time. Right? But remember, let's say they each have a toothed wheel and they both measure the speed of light. They agree it's the same speed. Now here's where things get really weird, is if they agree that the light with the same speed in two different frames of reference, but look at the distance that the light traveled. Isn't that a different distance for each beam of light? Huh, so wait, how could it be the same speed, but for two different distances? Einstein realized that the answer had to be that these two guys experienced different what? I gave you a big hint here with their stopwatches. Different amounts of time have passed, different times. Huh. And you can actually, I'm actually really close to showing you guys special relativity formula right here, because you can actually derive it from the geometry of this right triangle. You guys see the right triangle right here? So we've got three different distances. There's the distance light being traveled up to the mirror, just straight up. There's this diagonal distance, and there's also the distance that the train moved. So I'm going to label each one of those. The distance that the train moved would be speed times time, and it would be the outside guy's time, because the inside guy might have no idea that the train's even moving. Along with that same time is the diagonal motion of the beam of light. So I'm going to call that CT. And speed of light, C is the speed of light, right? So remember, C is 3.0 times 10 to the 8 meters per second. And everybody agrees on what that is. Right? Down exactly. So CT to travel this distance equals speed times time. But what about the distance like straight up to the mirror? Well, that would also be speed of light times time. But this CT and this CT can't be the same thing. I'm going to call it CT naught because that's the inside guy's time. Okay, so now, right? So you guys see right triangle? Do you think you could do Pythagorean theorem to relate these three terms to each other? So maybe something like this: CT quantity squared is equal to CT naught quantity squared plus VT squared. Okay. Isn't that Pythagorean theorem? Except, okay, so that relates these sides of the triangle. You know what I really like to know from this? This is special relativity right here. What I really like to know from this though is what is the relationship between these two guys' times? What is one guy's time in terms of the other guy's time? So what is this t, which shows up a couple places, in terms of this t naught? Let me do this. I think I got the derivation typed out on I do on a Word page. I can share my screen for you guys real fast here. I'll show you this. Right. So the top line looks exactly like what I have on the paper. Right. And then you go a bunch of algebra steps. And at the very last step, see what is t in terms of t naught. So what is the outside guy's time in terms of the inside guy's time? I know it looks messy, but it's divided by square root of, okay, this whole stuff in brackets is called the Lorentz factor. So I'm going to switch back over and write that out so it's a little bit neater. Share, back over. Okay. So could go through a bunch of algebra steps. I'm just going to save about 5 minutes here in class and say that the end result is this. The outside guy's time is equal to the inside guy's time divided by this Lorentz factor. 1 minus v squared on c squared. Okay. What's up? Guys get that? Okay. Now, I said you get to see this twice. So we're going to flip over to show you guys an animation version of this. You guys ever heard of something called the twin paradox? The twin paradox?